Doctor,
نعم.
the assessment is up to 14.7 or 14.6?
7.
Okay, thank you.
And you have this section and one more section. Okay. Okay. So let me just share the okay. You can see the page, huh? Okay.
Yes.
So just okay. طبعا let me mention something. You know, I recorded a video for the second point in section 14.5, which is the chain rule. The video recording is in the office hour Teams. So please go and watch it. And it is a short video, and it is a very simple point. Okay. Now we start a new section, which is directional derivative.
Sorry for interruption, but in the syllabus, it's written that it's up to 14.8.
Yeah, I know, but it is up to 14.7. Okay. Fee correction.
Fee correction.
Yes. Okay. 14.7. Okay. Okay. So now 14.6 directional derivatives. So the meaning of this will be clear very soon. So we'll leave it for a while. We go to the first point in this section, which is a mathematical term, which is called gradient vector. So let's define this mathematical term. Okay. So definition. The gradient vector of a function of xy, or we just say gradient of f, or the gradient of f is the vector defined as okay. So we have the following vector, which is the components of the vectors are f sub x, xy, and f sub y, xy. Okay, that is a vector whose component is f sub x and f sub y. The notation for the gradient is the following, where I just inverted delta of xy. Okay, this inverted delta is called del. We read it as del. Okay, so we say del of f, or we always say gradient of f equals f sub x comma f sub y. So this is it is a vector, and called a gradient vector of f. Okay. Now just a simple example here. Example. Let f of x y equals xy squared plus x minus 5y. Find gradient of f at xy and gradient of f at 1 and 2. Solution here. Okay, so to find the gradient, just apply the definition. Gradient of f xy. Okay, you have the definition, which is the vector f sub x xy, f sub y xy, and then compute f sub x and f sub y. What is f sub x? Again, differentiate with respect to x, looking at y as a constant. This هيكون y squared plus 1, and f sub y, look at x as a constant, هيكون 2xy minus 5. So this is the gradient of f. So the gradient is a vector whose components are functions. So here these are functions. Okay. If you want to find the gradient at a point x 1, 2, you just substitute. You set x equals 1 and y equals 2. N in the formula here. Okay. So this becomes 2 squared plus 1, 2 times 1 times 2 minus 5. And this is the vector 5 and minus 1. Okay. So this is the definition of the gradient, and this is how to compute it in general and how to compute it at a point. Okay. if for functions of 3 variables, you'll have f of x, y, z, then the gradient will be gradient of x, y, z. It is the vector consisting of the components f sub x, f sub y, and then we add the f sub z, okay, the extra component, the z component, f sub z, okay. But this is the definition of the gradient. Now, what is the importance of the gradient? What is the application? You will see it very soon, okay. In fact, in this section and in the next section, okay. So this is for the first point, the gradient vector, okay. If it is clear, write one in the chat. So it's just a definition of a mathematical term whose application will be seen very soon, okay. So this is the first point, okay. Now we go to directional derivative, the second point, directional derivatives, okay. This is the key point or the main point in this section, and for this, just to understand this, I will just make a review or a reminder of f sub x and f sub y, okay. F sub x at x0, y0, and f sub y at x0, y0, okay. So pay attention for this section. To understand this section or the main idea, we have just to recall the geometric meaning of f sub x and f sub y, okay. If you forget, no problem, I will recall it now, so pay attention, okay. Just try to understand the geometric meaning of f sub x and f sub y. If you know it, this section is over, okay. This section becomes very simple. So let me recall the geometric meaning of these two things. So this is the space here. This is x, and this is y, and this is the z-axis. You have a point x0, y0. This is a point x0, y0. Okay, and this is the surface. This is a surface. Z equals f of x, y. Okay, you have a surface. Okay. Now, for f sub x, for the geometric meaning of f sub x, it is the following, and that is partial derivative with respect to x. So x will be changing, okay. So in the domain, you move parallel to the x-axis, okay, parallel to the x-axis. Okay. So here y0, this is y0. So y is fixed, and you are moving parallel to the x-axis. So here x is changing. F sub x, the change with respect to x. So x is changing and y is fixed. This is always y0. So when you move, let me just before this, this is also this is off of x0, y0, off of x0, y0, okay. Now when you move parallel to the x-axis, y is fixed, y0, okay. So you are moving, the changing is in the x direction, So I am moving parallel to the x-axis through x0, y0. Now these points, what are the images of these points? These points, their image will be in the surface. There will be a curve. Okay. So these points have the image in the surface will be a curve. So I have a curve on the surface. And to this curve, there is a tangent at this point of x0, y0. This is the tangent. Okay. What is the slope of the tangent? It is the slope equals f sub x at x0, y0. Okay. And this is the geometric meaning of the f sub x. So this is slope of a tangent line to a curve resulting from the points when you move along or parallel to the x-axis. Okay. F sub y, now for f sub y, I will be moving parallel to the y-axis. So I will move in this direction here. What is the image of these points? It will be a curve on the y in the surface. This is a curve. So when you go on this along the red points here, you get a curve on the surface. To this curve, there is also a tangent. This is the tangent at x0, y0. Tangent. What is the slope? Slope equals f sub y at x0, y, y0. Okay. Okay. So this is the geometric meaning of f sub x and f sub y. Okay. I repeat, if you understand this, well, congratulations. This section is over. Okay. Okay. Again, f sub x, you just move parallel to the x-axis through the point x0, y0. These are the points. The corresponding image of these points will be this curve, and to this curve, the black one, you have a tangent line. The slope is f sub x. When you move parallel to the y-axis through the red points here, you have a curve, the red curve on the surface, and you have a tangent line. The slope is f sub y. Okay. This is the geometric meaning of f sub x and f sub y. Okay. Okay. Now, if it is clear, just write 2 in the chat. This is just a reminder. Write 2 in the chat if this is clear. This is the main point. Just recalling the geometric meaning of f sub x and f sub y, and I already recalled it. And if you forget it, no problem. I just recalled it. Now, okay, now this section, for this section, pay attention. Now for this section, well, there is a natural question, okay, which is the following. Well, here you move along parallel to the x-axis and parallel to the y-axis. Well, can I move in another direction or not? And for example, can I move in this direction here? Okay, some direction. Let me call it the direction of some vector u. Okay. Can I move in this direction? The direction of u is. The answer is yes. You are in the plane. You can move in any direction. So can I move in this direction? Yes. Okay. Now, when you move along this direction, okay, you will have a curve, a corresponding curve on the surface. So this is h the curve. This is h the curve. Okay. So the image of these points along u or parallel to you in the direction of u will be this green curve. Now for this green curve, again, there is h, a tangent line. So this is the tangent line. Tangent line, okay. And for this tangent line, it is natural to say, what is the slope? What is h? The slope. Okay. It is very natural to ask, what is the slope? Okay. Not only this, you choose this direction. I can choose another direction. For example, this direction here. Okay, I go just move in this direction. You will have a corresponding curve, and then a corresponding tangent, and then you will ask what is the slope of the tangent. Okay, you have infinitely many possible directions. You can move in the domain and through or in infinitely many directions, and in each case you will get a curve and then a slope, and then you ask what is the slope, what is the slope of the tangent. Okay, so this is h, the main question here. Okay, now for when you move along the parallel to the x-axis, the slope will be f sub x, partial derivative. It is called partial derivative with respect to it. When you move along the y-axis, you get h slope of a tangent, which is called partial derivative with respect to y. When you move in another direction, for example, direction u, the slope, it has a specific name. It is called directional derivative, directional h derivative. Okay. The title of the section, directional derivative, i.e., derivative in a direction, derivative in a direction, and a derivative in a direction u, in the direction of the vector u. Okay. So this is still always the slope will be derivative, but now this is generalization really of f sub x and f sub y. And now instead of going parallel to the x-axis or parallel to the y-axis, we are going in a specific direction u. So the slope will be derivative in a direction or directional derivative, directional h derivative. Okay, this is what it is. Okay, this is the geometric meaning really of directional derivative. Now, what is the formal definition? Now, the formal definition is the following. Okay, so you know the situation now geometrically. Let's just write the meaning algebraically. Okay, so definition here. The directional derivative, i.e., derivative in a direction, of f at x0, y0, in the direction of the unit vector. It is very important when you say direction, it has to be a unit vector, as was mentioned in section 12.2. Direction not unit vector. Okay. In the direction of the unit vector u equals u1 u2 as defined as. Okay. This is the obvious or the natural definition. It is the limit definition. What is the limit definition of the directional derivative? For always we start for derivative, the definition always will be in terms of limits. So here this is h limit as h approaches 0. Okay. Of something minus of x0 y0 over h. Okay. What is the here حتكون هنا x0 plus h u1 y0 plus h u2. Okay, u2. I will explain now why I have this x0 plus h u1 y0 plus h. I will explain it very soon. Okay, but here from the definition you notice هنا you have a directional derivative. You have a change in both coordinates, a change in x coordinate and a change in y coordinate. For partial derivative with respect to x, they change only in x. For partial derivative with respect to y, they change only in y. Okay, in y. Here for directional derivative, in a general direction, you have both changes in x and you have changes in both coordinates, x and y. Okay, this is a distinction. Okay, or you can say it is generalization really of f sub x and f sub y. What is the notation? It is capital D for directional derivative of f at a point x0, y0 in the direction of the vector u. Okay, in the direction of the vector u. This is the notation. Okay, so this is the algebraic definition. This is the algebraic definition, the limit definition of directional derivative. Okay. Now, why we have the changes here? Just let me explain why you have x0 plus hu1, y0 plus hu2. It is given as follows. So here I am working in the domain. So this is h. So I will just go in the xy plane, x and y plane. I have x0, y0. This is x0, y0. I am moving in a direction. This is h, my direction, u. Okay. Now, when you move in the direction, I move a distance of h. When I move a distance of h, I reach a point x1, y1, x1, y1. Okay. x1, y1. So the limit of a final minus of initial over h, of a final minus of initial over h. Now, what is the relation between x0, y0, x1, y1, and the vector u? So I have in a b0 here. Let me call it b0, and this we call this one b. What is the relation between them? I have b0b, the vector, and the vector u. What is the relation between them? Okay, they are h parallel. They are parallel. They are parallel. If they are parallel, معناته they are multiples of each other. B0B equals KU. Okay. Now, if you are moving a distance of h, then what is the K? It will be h. Okay. K will be h. Okay. Okay. So this becomes B0B equals h times the vector u. Okay. So this implies x1 minus x0, y1 minus y0 equals hu1, hu2. Okay, hu2. Okay. Now equate يعني combine حيكون x1 minus x0 equals hu1, y1 minus y0 equals hu2. So this is like x1 equals x0 plus hu1 and y1 equals y0 plus hu2. Okay. So when you move a distance h, you get a new point x1, y, which is x0 plus hu1, y0 plus hu2. And this explains the definition here. When you move a distance of h, you reach this point from x0, y0 to this point. Okay. So of a final minus of initial over h. Okay. So this is h, the justification of this definition. So this is the h definition, the limit definition of directional derivative. Okay. Now here we notice from our geometric introduction here, and really the directional derivative is a generalization of f sub x and f sub y. Just you are moving in a different direction. Okay, Geometrically, the directional derivative is a generalization of the partial derivatives f sub x and f sub y. Geometrically. Now, is it a generalization algebraically, and using the definition or not? So note, note. If I choose the vector u, the unit vector will be I, to be I, which is h1 and 0. Which is along the x-axis, okay. What is the directional derivative of f in the direction of I? At x0, y0. Directional derivative, I have to apply the formula here. So this is limit here, as h approaches 0, of f x0 plus h times u1. What is u1 here for I? 1, it is 1. So u1 will be 1, comma, y0 plus hu2. u2 is 0. هتكون just y0. Minus of x0, y0 over h over h. Okay. What is this equals to? What is this limit here? Just there is a change in x only. There is a change in x. So what is it? Since x only changes, then the whole thing is just f sub x. x0, y0. The same thing if you choose u equals j. If you choose u equals j, if you choose u equals j, which is h01, in fact, the directional derivative at x0, y0, when you apply the limit, you get f sub y, y0. So this means what? Really, the partial derivatives with respect to x and with respect to y are special cases of the directional derivative, or the directional derivative is a generalization of the partial derivatives f sub x and f sub y. So directional is just generalization. Okay. So this is now the definition of the directional derivative, and this is the geometric meaning of the directional derivative. Still, it is a slope of a tangent line to a curve, but in a specific direction. Okay. Okay. Now the next step, which is the main thing, in how to compute directional derivative. Computing directional derivative. Let me see here. Theorem here. Theorem. Computing directional derivative. Directional derivative. Directional derivative is a generalization of partial derivative. For partial derivatives, f sub x and f sub y, we know a rule how to compute it. To compute f sub x, you look at y as a constant, and you differentiate with respect to x using the rules of math 101. To compute f sub y, I look at x as a constant, and I differentiate with respect to y using the rules of math 101. Now, what about directional derivative? Here, for directional derivative, you have also a general rule, okay? And the rule is given as follows. Directional derivative of f at x0, y0 in the direction of the vector u. It is given as follows. Gradient of f at x0, y0 dot the vector u. It is the gradient dot the vector u. So it can be computed using the gradient, the one we just introduced. Okay. Well, how to prove this one? We will not give the proof, but really the proof follows from the limit definition. Okay. When you use the limit definition and you play with it, you get you end up with this formula. Okay. The proof is given in the note. If you want, you can read it. But in fact, it is optional, let me say, okay. At the end, you have a formula to compute the directional derivative. Gradient dot u. But always a very important thing, make sure the vector u is a unit vector. Okay. This is a common mistake students make, okay. In the formula, in the definition, and in the formula, u is a unit vector. Okay. Let me give you an example of how to apply this, and also how to apply this note. Example here. Example. Find the directional derivative. Of xy equals 2xy to xy minus 3y squared at the point 5, in the direction of the vector v, which is 4 and 3. 4 and 3. Okay, solution. So pay attention, and things are really not difficult. I need to compute the directional derivative. Can you give me the brief answer for computing the directional derivative? How to compute the directional derivative? I need a brief answer. Okay.
Formula.
Apply the formula. I have a formula. This is the formula for computing the directional derivative. It is the gradient dot the vector u. Okay. Once you have a formula, life becomes very simple. Just go and apply the formula. We are telling you how to compute it by this formula. So to apply this formula, I need to compute the gradient first. So first, let me compute the gradient of f at xy. And this is h, the vector f sub x at xy, f sub y at xy. I have f. Yes, I know how to compute f sub x and f sub y. What is f sub x? F sub x will be h 2y, and f sub y هيكون 2x minus 6y. Okay. You should know how to compute f sub x and f sub y. I need the gradient at the point x0, y0. Here the point is 5 and 5. So the gradient of f at 5, 5. Just substitute x equals 5 and y equals 5. This becomes h 2 times 5, 2 times 5 minus 6 times 5. And this is h 10 and minus 20, okay, minus 20, okay, it is okay. But this is the gradient. Now the vector, I need the vector given here is v, which is h4 and 3. What should I check now? What should I check for v first? What should I check for v?
Whether it's unit
It has to be a unit vector. Yes, okay. Notice the formula, the vector has to be a unit vector. Okay. So check, is it a unit vector or not? Well, how to check? Just find the magnitude of the vector v. Root 16 plus 9, which is h5, which is not equals 1. So I have to change it to a unit vector. So how to change it to a unit vector here? You just divide by the magnitude, which is h1 over 5, 4 and 3, and this is h4 over 5 and 3 over 5. Okay, this is h, the vector. Okay, so I change it to a unit vector. You give it a name u, for example. So now directional derivative of f at 5, 5 in the direction of v. It is the directional derivative of f at 5, 5 in the direction of u. So I go from v to the unit vector. Okay. Now I have the formula gradient of f at 5, 5 dot the vector u. So use the dot product. The vector is h10 and minus 20 dot the vector 4 over 5 and 3 over 5. This becomes 40 over 5 minus 60 over 5, and this is minus 20 over 5. Okay, which is minus 4, which is minus 4. Okay. So this is how to compute the directional derivative. You have a formula. It is very simple. Just make sure the vector is a unit vector. Okay. This is the directional derivative, the definition, the geometric meaning, and how to compute it. Okay. If it is clear, please write 3 in the chat. Write 3 in the chat.
دكتور.
نعم.
بالنسبة ل f sub z راح تكون generalization صح ولا؟
نعم. Just you add the z component. Yes. Okay. So as you can see, it is really a simple concept, directional derivative. Just a generalization. Briefly, a brief answer for the directional derivative is just a generalization of the partial derivatives of sub x and f sub y. This is really what it is. Okay. Now we have one question about directional derivative. Pay attention to the question. We'll mention the question and then we'll mention the answer to the question. But it is very important to understand the question. Okay. Once you understand the question, you will see the answer. At the end, it will be given by a formula. We'll explain the formula also. So pay attention to the last thing, a property about directional derivative. Okay. So pay attention to the question. Pay attention geometrically. So this is at a point. طبعا هنا our question always at a point x0, y0. Okay. As given here in the, so you have x0, y0, x0, y0. This is f of x0, y0. Okay. Pay attention. The question is the following. Okay. Again, when I move along the x-axis, parallel to the x-axis, I get the black curve. I get then a black tangent, and the slope is f sub x. Okay. When I move along the y-axis or parallel to the y-axis, I get the red curve, I get a red tangent, and the slope is f sub y. Okay. When I move along the vector u in the direction of the vector u, yani the green direction here, I get also a green curve. I get a green tangent line, and the slope now is known. The slope is directional derivative. So the slope here, directional derivative at x0, y0 in the direction of u. Okay. So now I know how to compute the directional derivative. So these are the three directions or three curves or three tangents or three slopes given in the graph. As we mentioned before, I can use other directions in any direction I want. I can use, in fact, I will have infinitely many directions. And in each direction I choose, I will have a corresponding curve, then a corresponding tangent, then a corresponding slope. Okay. And you repeat the same thing for other directions. At the end, at x0, y0, at the end, you will end up with infinitely many tangent lines, and hence infinitely many slopes, infinitely many tangent, and hence infinitely many slopes. Okay. Now the question is the following: what is the largest slope and what is the smallest slope? Okay. What is the largest and what is the smallest? Don't give the answer. Make sure now the question is clear. Okay. Is the question clear or not? So our question here, I will repeat again. When you move parallel to the x-axis, I have a black curve and then a black tangent, and I have also a slope, which is f sub x. When I move parallel to the y-axis through the red line here, I will get a red curve, a tangent curve, and a slope f sub y. When I move along a vector, the direction u, along the direction of the vector u, I get a third curve, a third tangent, and get a slope. I continue the same thing because I can move in infinitely many possibilities, okay, in infinitely many directions. And in each case, I have a tangent, I have a curve, then a tangent, then a slope. So eventually, at a point x0, y0 here, I will have infinitely many tangent and so infinitely many slopes. The question: what is the largest slope? What is the smallest slope? Okay. Is the question clear to you? Is it clear?
Yes, it is clear.
Okay. Question should be clear. It is not. You didn't need to be a genius to understand that question. Now we need to get the answer now, and we give you the explanation. So what is the answer to our question here? So the answer is the following: at x0, y0. Notice we are specifying a point. So you have different answer at different points at x0, y0. The largest slope of the tangent, or we say maximum value of the directional derivative, Okay, the largest slope or maximum value of directional derivative, or also in Math 101, derivative means rate of change. We can say what is the maximum rate of change. Largest slope, maximum value of directional derivative, maximum rate of change. They are all, they give us the same thing. The answer is the following. The largest slope is the following. It is magnitude of the directional derivative of the gradient of the function. Okay. This is the largest slope. Okay, this largest slope, when you find the largest slope, also we need to know in which direction this largest slope occurs. In which direction, okay. So here, and it occurs in the direction of it is the vector u, which is in fact the direction of the gradient. In the direction of the gradient. But I need the direction to be a unit vector, so I have to divide it by the magnitude just to make it a unit vector. Okay. So the answer is given in terms of the gradient. In terms of the gradient, the largest slope, magnitude of the gradient of f at the point x0. In which direction? In the direction of the gradient. You take the gradient and divide it by the magnitude just to make sure it is a unit vector. Okay. This is the largest slope. What is the smallest type? Smallest. Okay. It is the same. Not exactly. You see. What is direction? Direction. Where it occurs, it is the same. Okay. Okay. Not exactly the same. There will be a change. Okay. So this is when you copy and paste. So the smallest will be what? It is the negative. It is the negative. The direction, the negative. Okay. So هنا positive هنا ايش negative. Okay. The largest will be positive, the magnitude. Smallest negative, the magnitude of the gradient. Direction, the same, gradient over magnitude, and a negative, the gradient. Okay. This is the largest value for the slope and the direction for the largest and smallest. Okay. This is the answer. This is the answer. Okay. Now we need to know, يعني في النهاية you have a formula for the answer. Okay. So when you have a formula in the next, when you give you an example, find the largest slope or find the maximum value of a directional derivative, you have the answer is given in terms of you, in the front of you. Okay. This is the answer for the value and the direction for the largest and the smallest. Okay. So I will not give example. I will leave the example for you to read in the note, but I will give you now explain. I have to explain this one, why this is the largest and why this is the direction. Okay. The example, direct application of the formula. So let me explain why this is the answer. Why this is the answer. Okay. For now, the largest value of the slope or the maximum value of the directional derivative. So I have to go to the directional derivative. This is the directional derivative. At x0, y0. I have to find the largest. I have to study the formula or the value of the directional derivative. It is given by the gradient of f at x0, y0 dot the vector u. This is the formula for the directional derivative. It is use the dot product from chapter 12, actually gradient of f at x0, y0 times magnitude of u times cosine theta. Theta is the angle between the two vectors u and the gradient. Okay, this is how to compute the gradient, how to compute the directional derivative. What is the magnitude of u? What is the magnitude of u? Okay.
Unit vector and
one. It has to be one because it is a unit vector. If u is a unit vector, its magnitude will be 1. So this becomes magnitude of f at x0, y0 times cosine theta. Now we know that cosine theta is between 1 and -1. I will multiply through by the magnitude of the gradient. So this gives us the following: minus of x0, y0 less than magnitude x0, y0 less than magnitude of cosine theta less than magnitude of f at x0, y0. Okay. So when you multiply by the magnitude of the gradient, I get this one. Now, what is this equals to? This is directional derivative. of f at x0, y0. Because this is equal this one, which is h, the directional derivative. Okay. So this is less than or equal magnitude of f at x0, y0, and minus magnitude of f at x0, y0. Okay. Okay. So what can we conclude from this one? Notice the value of the directional derivative is between these two values. Okay. The value of the directional derivative is between negative the gradient, negative magnitude of the gradient, and magnitude of the gradient. Okay. So question. So what is the largest possible value of the directional derivative? Okay. What is the largest possible value? What is the largest possible value? It is this one. This is because it is less than. So this is the gradient, the absolute value of the gradient. What is the smallest possible value for the directional derivative? This is the smallest possible value. Okay. This is the largest, and this is the smallest possible. Okay. So the value of the directional derivative lies between these two values. So this is the largest possible, and this is the smallest possible. Okay. Notice I said possible, largest possible. Now I need the largest. I do need the largest possible. Okay. I need the largest. Okay. So I ask myself, can I have equality? It is here. It is less than or equal. Can I have equality here or not? Is it possible to have equality here? Okay. Is it possible or not? You check. Now this is h gradient, magnitude of f at x0, y0. And the directional derivative is this one with the cosine, just bring its value. So this is h. This is of x0, y0, cosine theta. So is this possible? This side here, gradient cosine theta. Is it possible for it to be just equal the gradient? Is it possible or not? Okay. When is it possible? Okay. When cosine theta is equals h.
1.
1, if it is 1. If this is 1, then they are equal. They are equal.
When theta is equal to 0.
Okay. Now cosine theta. Is it possible for cosine theta to be 1? When
Yes.
theta is what age? Okay.
0 and 2 1.
Okay, no. طبعا you remember from the sections on vectors and the angle. The angle is by definition to could between between 0 and pi. Okay. If you remember this one. Okay. The section, the definition for the angle between two vectors, you remember which was the smallest angle. Okay. It will be between 0 and pi. This is a restriction on theta. So cosine theta equals 1. It is possible when theta equals 0. When theta equals 0. Okay. So if theta equal to 0, I will get equality. So it will be the largest possible value. It will be the largest possible value. Okay. Okay. So if theta equal to 0, I get the largest value here, magnitude of the gradient. Magnitude of the gradient. Okay. But this is the answer. Now, in which direction will it occur? Okay. Okay, I go back to the definition here. Now, dot gradient, directional derivative equals gradient dot u. And theta is the angle between u and the gradient. If theta equal to 0, this is what we found. If theta equal to 0, then what can we say about u, the direction of u and the gradient? What is the relation between them? Okay. If theta equal to 0. The angle between them is 0. The angle between u and gradient is 0. This means what? Okay.
They are parallel.
More than this. They mean they have the same direction. If theta equal, they have the same direction. So if they have the same direction, then I can choose u to be just the gradient. Okay. I can choose u to be the gradient. Okay. But I need u to be a unit vector. So what do? You divide it by the magnitude. Okay. But this is the answer. Okay. So the largest magnitude of the gradient. U, the direction, it is just the gradient. I can take it to be the gradient. But I need it to be a unit vector. You divide by the magnitude. Okay. But this is the justification for this one. For the smallest, you do exactly the same thing, but you work on the other inequality. You work on this. You work here. You work here now. You get cosine theta equals -1, then theta equals pi, then the angle, they are opposite. They are opposite, okay. Or the angle between them So they are negatives of each other. You get H, the negative sign, because theta will be pi here. Okay, and you get H, the smallest. Okay, this is H, the justification. This is the proof for the largest and the smallest. Okay. In the example, as I mentioned, it will be clear. You have a formula. Just go and apply the formula. Okay, and this is H, the answer, and this is H, the formula. So I will leave the example for you to read it from the note. You have a formula, a direct application of the answer is a direct application of the formula. Okay. Now this is H. This is what we need to know about directional derivative. If you have a question, you can ask. If you didn't have any question, have a nice day. Don't forget you have this week a quiz. Okay. On Thursday, check the announcement in Blackboard. Okay.
What does gradient mean in Arabic?
يعني later شوف يعني when you leave high school you don't see the translation of many terms. عرفت؟ واضح؟
صحيح.
يعني هاي you don't see them يعني they available يعني the translations are يعني usually for the mathematical terms that are used in high school and before. After you leave you don't see them. Okay. بس gradient ممكن تكون له معيار مثلا أو شيء كذا. grade يعني كحاجة مقياس معين يعني. أوكي. واضح.